From the introduction of transformers, we can start to actually analyze some circuits now. So we're going to consider a circuit where we have a voltage source equal to 12 volts with a phase angle of 0 degrees. On the input, we're also going to have a capacitance with an impedance of minus J4 ohms. Our inductor value is going to be J5 ohms. And that's going to be our primary side. On our secondary side, we're going to have a J6 ohm inductor and then a 12 ohm load. Now we're going to be coupling these together with a mutual inductance of J3 ohms. We're going to have currents labeled as I1 and I2. So the first step that we're going to do is mark our polarities independently, and that is here in the black. So we know we have a voltage drop over this capacitor, and if our current is going clockwise, we have a voltage drop over this inductor. Now on the other side, we have voltage drops over both components because our current is going clockwise, so we label those accordingly. And then the second step is to analyze the dots. So we were given that the current is going clockwise in the primary, so it's going into the dot. And we know that this current going into the dot is going to induce a positive voltage reference on the other dot of the secondary. So in red, we draw the polarity as follows. And if we look at the second coil, current comes out of the dot or it goes into an undotted terminal. So it will induce a polarity that matches as we've drawn here. So we know that I1 induces this positive polarity here for the secondary inductor, and likewise for the primary inductor, how I2 induces that voltage. Now if we look at the inductor on the primary, it looks a little bit odd because on one side it looks like you have a voltage drop, but on the right side it looks like you're actually going up in voltage if you keep a clockwise notation. So this is where we start to write our KVL. So we would start with our voltage, and then we would have a voltage drop for the minus J4 plus J5, which are on the primary side, and that's times that first current I1. But because of this induced voltage, you actually get a plus, and then I2, and where the value that you multiply that by is J3, which is the mutual inductance that we were talking about in the previous video. And if we look at the secondary loop, you would have minus I2 times the sum of those impedances, and then you have plus I1 times J3. These plus signs are because of this flipped polarity for each of the inductors. So it's a brand new notation and way to analyze circuits, so it might be a little bit confusing at first. The more examples you do, the easier it becomes. So plugging in these values, we can simply use substitution to find that I1 is equal to 13.01 amps with a phase angle of minus 49.4 degrees. And we can find that I2 is equal to 2.91 amps with a phase angle of 14 degrees. So going up in difficulty, we're going to look at a harder example where we don't just have a load on the secondary, we also have a voltage. So we're just going to call a primary voltage and a secondary voltage. So if we have our current labeled clockwise, again, we're going to get a voltage drop over R1, voltage drop over L1, and we have current entering the dot here. So current entering the dot on the primary will leave a positive voltage reference on the secondary at the dot. So we get the plus and the minus here. Now if we look at the secondary, we have a voltage Vs. We're going to have a voltage drop over R2, voltage drop over L2, and from here we have current entering the dot, I2. So current, again, entering a dot at one of the sides will induce a positive voltage at the other dot. So now we get a plus here and a minus here. And again, if we focus on L1, now it looks like we have a voltage drop due to I1 and a voltage drop due to I2 here in the red. So writing a KVL around the left-hand side of the transformer, we get Vp minus I1 times the sum of these impedances. And then because we have a plus and a minus right here, we have that additional voltage drop due to I2. That's going to be equal to J omega times the mutual inductance right here. If we look at the secondary, similar process, we have Vs minus I2 times the sum of the impedances. Again, we have a voltage drop induced from I1, and that's going to be equal to 0. So substitution, we can solve for these equations and simply get I1 and I2. And we can also define that mutual inductance as K times the square root of L1 times L2, where K is just going to be this coupling coefficient. Now if K is equal to 1, we have an ideal case. Not likely the reality, but for analysis, it's okay. If K is less than 0.5, we have a poorly coupled transformer. And if K is greater than 0.5, but less than 1, it's a strongly coupled system. And from this, we often simplify the circuit even further. So we're going to consider that K is equal to 1. We're just going to look at the primary and the secondary windings. So we're going to have current going into a dot, which means we are going to have a positive reference at the other dot here in red. And we know that this current that's leaving the dot can also be expressed as current going into an undotted terminal, which will have a positive voltage reference at the other side of the undotted terminal. So we get polarities that look like this for the coupling. Now from this, we're simply going to do a KVL, for which we can use substitution to solve for the primary current, for which we can manipulate equation 1, plug it into equation 2, and arrive at this term here. Now from this equation, we're simply going to substitute our value for M and our value for K to arrive at the secondary voltage equal to this term here. And with that substitution of K equals 1, simplifies pretty nicely that we get the secondary voltage equal to the primary voltage times this factor, which is the square root of the second inductor divided by the first inductor. Or we can say that the secondary voltage divided by the primary voltage is equal to that square root of the ratios of the inductors, which is also equal to N2 divided by N1, which are the individual turns of each inductor. But all of these values are going to be what we define as the turns ratio. And we're going to call the turns ratio A, which is going to be equal to N2 divided by N1, or the square root of L2 divided by L1. There's a lot more that we can define from the turns ratio, and the turns ratio is actually going to make solving transformer problems pretty easy. But we'll see that in the next video.